and also adaptation. Continuing our theme of codes, I'll talk about algorithms for decoding codes, also derived by approved systems. And this is something we've been working on for last few years with some fantastic authors. All of them seem to be moving. Okay. So, and yeah, please stop me at any point if something is unclear in the back. So, I use a slightly different notation for codes and so on. So let me just kind of set up notation, also just remind you the definition. So I'll just think of a code as just a subspace of, let's say, F2 to the n. I'll not worry about the message. I'll only think about code words. So we'll just think of this set of code words and we'll think of linear code. So this set is a subspace. More generally, you can think of a larger field size or FQ. Q is not query, it's the alphabet size or the size of the field, and the number of bits in the code, which we call block length, is noted by capital N. And just think of a subspace. The problem of decoding a code, again, we are not working with local decoding, we just kind of have the full amount of time we want to take for decoding. And in general, the problem of decoding is recovering from corruptions. And the number of corruptions we can recover from is governed by a parameter of the code, which I'll denote here by delta. Again, it's slightly different from delta in probation stock. It's not the number of corruptions, but it's the distance between any two code words. And we'll measure distance in terms of the fraction of bits in which they differ. So fractional Hamming distance, it will be a number between 0 and 1. And if we want to uniquely recover the nearest code word. So suppose I tried to send you a code word, there were some corruptions, and you want to figure out which code word I intended to send without any ambiguity. The best I can hope for is delta over 2 fraction of corruptions. Because otherwise, I can corrupt so much that the closest, or sort of, you go from this center to something closer to this center, and then there is no way to resolve this. So if I want to uniquely identify what was sent, the best number of fractions, the best number of corruptions I can recover from is delta n over 2 or delta over 2 fraction. And we'll see a little bit of an update on this, but are we okay with this so far? Okay. Delta, again, to remind you, will always denote the distance of our code. And of course, the fact that I can do it doesn't mean that I can do it efficiently. And there is a sort of highly non-trivial algorithmic problem, which is, if I give you something which is a possibly corrupted version of a code word, can you find the code word that I intended to send? And again, in this global setting, you can find the message and then encode it yourself, or you can find the code word. It doesn't matter. I mean, we have enough time to write down the entire code word. And I'll actually talk about a generalization of this problem, which Marco asked about in the last talk, which is list decoding. So, yeah. Thanks for that. So list decoding is a problem where, let's say I'm trying to deal with corruptions which are more than delta over 2. So now I can't hope to uniquely find the code word. Let's say if you sent me something, I can't hope to uniquely identify it if there are more than delta over 2 fraction of corruptions. But maybe I can give you a small list. Maybe I can say that here are these 5 possibilities, and was one of them what you intend. Okay. And more generally, this has a lot of applications in complexity theory where we don't want to recover the code word with complete success probability, but with some positive probability. So I can pick a random element of the list. If the list is small, this will be useful. And now there are 2 problems. One is combinatorial. I need to actually prove just by analyzing the code that the size of this list or the number of possibilities is small. And the second is still this non-trivial algorithmic problem, which is, can I find these codes? Everyone okay with that? So the combinatorial problem is, in some sense, the solution is known, a general one for every code, so that there is a parameter rho which depends on the distance. And this is something which I'm denoting a function of delta, j of delta. It's called the Johnson bound, which is somewhere between delta over 2 and delta. And then, so the unique decoding radius and the distance of the code, which is the maximum we can hope for. And up to rho fraction of corruptions, we do know that the size of this list is small for any code word. This row depends on delta. Delta is the distance of the code. So there's some bound depending on the code where we know the size of the list is small. And even here, there is a non-trivial algorithmic problem of finding these code words. And I mean, there are codes which we do know how to decode all the way up to the Johnson bound, but this is largely an algebraic phenomenon, as Pravesh was saying, maybe some kind of algebraic magic and things like Reed-Solomon codes. If you want really good codes, then you need to work with very large fields and then use some things like algebraic interpolation. And in this talk, I want to maybe discuss maybe a slightly different way of thinking about list decoding, which doesn't rely on this kind of algebraic phenomena and also can apply to codes where we did not know list decoding algorithms before. And this will go through basically implementing the proof of some properties of the code as just an algorithm. So I'll tell you what the Johnson bound precisely is. I'll tell you how to decode, but is everyone okay with the list decoding problem? And so the fact that combinatorially we are at least okay if you believe me about the Johnson bound, and then we'll focus on the algorithmic problem of finding these codes. All right. So the codes I'm going to talk about will be based on expander graphs. And again, let me just remind you, or at least present the notion of expander that I'll focus on in this talk. So we'll always think of, let's say, D regular graphs. D will be a constant. So we can just think of it as fixed, small constant. And I'll call this graph a lambda expander if the second eigenvalue of the normalized adjacency matrix, so we divide by 1 over D, so the eigenvalues are between -1 and 1. The largest one is 1. You can use the all ones vector to check that. Okay. And the second one, if it's less than equal to lambda, I'll call this graph a lambda expander. Everyone okay with that?
Do we care about absolute values or?
No, not in this talk. I'll just only look at the second one just below 1, just on the real line. Okay, there is a long history of codes associated with graphs and in particular expander graphs, and these were also specifically things called LDPC codes. I mean, I'll mention that in a minute, but I mean, this is already an abbreviated version of the history, and I'll actually just focus on some specific points on this. So there's a beautiful construction of codes based on expander graphs, which derive their property of distance for the code and hence the bounds on how many errors you can correct, etc. From using the expansion of the graph. They come with beautiful, elegant linear time encoding and decoding algorithms for unique decoding. And we'll talk about list decoding of these codes, in particular, because they're constructed from some combinatorial phenomena like expansion. We don't have some of the algebraic things that are usually used in list decoding available for these. And I'll actually focus on a slightly simpler version of this construct and use more, which is a little easier to use. And here's the construction. So, and again, we'll not use a lot of specifics about this construction. This is just something to keep in mind. The kind of paradigm I'll talk about applies more broadly to, we'll see when it can apply, but this is a specific example to keep in mind. And this is constructed in terms of a base code. So let's fix code C0, which is a constant size object. It lives in F2 to the D. It's just something which is kind of given to us. We can search for it, fix it, and then use whatever properties we need. And using this small code, we'll actually construct a much larger code, which we will think of as sitting on the edges of a deregular bipartite graph. So let's say we pick a bipartite graph with n vertices on each side. It's deregular, and we'll take it to be an expander. And because it's bipartite, the eigenvalues will be symmetric about the origin, and then we can just worry about the lattice one. And a set of sort of a sequence of bits written on the edges are said to be a valid code word. So the number of bits will be d times n, which is the number of edges. And we'll say that this is a valid code word if what every vertex of this graph sees, which is just a sequence of d bits, at every vertex, if it looks at the edges incident on this vertex. So these d bits belong to this base code. And you can, if this base code you think of as a subspace, so it's a linear code, so you can write whatever you want for this vertex, that these d bits belong to this code as a linear constraint. So we have 2n linear constraints, and they define a subspace. Okay? And if you choose parameters of the code right, the subspace can be shown to have good dimension, and then you can use expansion to prove large distance, etc. We'll get to that. But this is called an LDPC code. I mean, LDPC just means that it can be written as a kernel of a sparse matrix. And you can see that each of these constraints is written in terms of this matrix H, which is just in d dimensions. So each constraint involves only d variables, or at most d variables. So you can think of this entire code as the kernel of a sparse matrix. Again, that will not be important for the talk. It's just one property of these codes that was relevant, and then so they were defined this way, and then kind of also relevant in later constructions based on. Is the definition okay? Yeah.
It's probably not a question to you, but why it is important that it is bipartite?
So it's not. It's just slightly simpler to work with it, but you can also define it on just a deregular graph. It
And
doesn't have to
most things will work out, right?
Yes. Yeah, it's not. It's just slightly simpler to design. Any other questions?
So the
Yes, sir.
code word is like the bits live on the edges.
The bits live on the edges.
So the code word will just be the edges in some order, and it's sort of globally the code word is okay if every vertex on the edges around itself sees a code word in the smaller code.
Exactly. Okay. Yeah, so that's the definition of this code. I mean, so yeah, if you want to check if something is a valid code word, we can check it just kind of locally. Every vertex can just check what is happening around it. This is not a robust test by any means. If something is close to a code word, this test may fail terribly. But at least if something is perfectly a code word, we can check it this way. Any other questions? Okay. And just to say that this construction has lots of extensions. It's a very kind of widely used idea in lots of other interesting objects, and in particular kind of defining codes over reals or quantum codes or locally testable codes. And these are sort of objects which are kind of using much more sophisticated versions of this construction, and you'll be able to say some things about some of them, but I don't want to worry about that. So let's get back to these codes. And let me just do a very brief history of what is known about decoding them. Okay. So as I already said, there are beautiful algorithms for unique decoding of these codes. They are even parallelizable. They can run in linear time. And there are also algorithms which are based on linear programs, so relaxations and message passing, whatever. And even though the codes have been known for a while, we don't know, sort of at least, we didn't know of any kind of list decoding algorithms for these codes. And as I again said, the techniques for list decoding rely on some algebraic phenomena which are not necessarily available. One thing I do want to point out, there are list decoding algorithms known, I mean, or even fast list decoding, linear time list decoding algorithms known. If you're dealing with what are called erasures, which means that you know the look, you sent me something and I know that the errors are in the first, third, and the 15th position. So I know the location of the errors. And in this case, fast decoding is the interesting problem. I mean, list decoding is just Gaussian elimination, because I know that 3 of the bits of this subspace are garbage, or sort of I don't know what to interpret them. So I can just substitute them by variables and just solve for those variables. So list decoding is just Gaussian elimination. The important part is these papers can do it fast. But in the error setting, we just don't know even how to do it in sort of anything less than just kind of brute force searching over the exponentially many codes. And so we'll talk about list decoding when we don't know the location of the errors, which is the interesting thing. Doing okay? All right. So the result I want to talk about is an algorithm for list decoding these codes, and really a framework which applies more broadly. And you can decode all the way up to whatever is the Johnson bound till the point where we do know that the list size is bounded. And it basically is an algorithmic implementation of a proof of the Johnson bound. And we can sort of basically look at the certificate of distance of these codes, implement it in some sort of a proof system which can correspond to algorithms, in particular the sum of squares proof system. And this is a specific application of a broader paradigm of proofs to algorithms, which has been used quite a lot in statistical problems. And there is a nice survey by Noah, Pravesh, and Tony. This is one application of this to the setting of codes. Right. So is the result okay? All right. And so all I want you to maybe hopefully take away from this code is some proof of the Johnson bound. We'll do a slightly different proof from the usual one, and it's not too difficult to actually convert it into an algorithm. So let me tell you what the Johnson bound is and maybe give you a short proof. And then I'll say how to convert that into an algorithm.
This is the standard one or is your new one?
Sorry?
This is the standard one or the new one you have?
This is the one we have, which is, I couldn't find this particular proof in the textbook, but I mean, as you see, it's not a very complicated proof. So it's, yeah, I'll mention. But it adapts nicely to algorithms. Okay, so let me first tell you what the Johnson bound is or what the statement is. The Johnson bound, you can think of it as, well, not just think of it, it is some function of delta. And you can also write some function appropriately over larger fields. And I want to think about it this way, which is g of delta is some function such that 1 minus 2 times g of delta squared is equal to 1 minus 2 times delta. And it comes with the guarantee that for any point in this f2 to the n, if you're looking at the set of code words which are within distance j of delta to x, then the number of such code words is small. Okay? Remember, delta depends on the code. So delta is the distance of the code. You'll see a reason for this expression in a minute, but just some examples. So if you think of a code with distance close to half, the Johnson bound, which is optimal, like half is optimal for binary codes. The Johnson bound can be much larger than the unique decoding radius. And it's even more stark when you look at somewhat larger alphabet. The distance can be close to 1, but the unique decoding radius can never exceed half. So, and let me prove it. But any questions about the statement? I'll prove it by a statement which I'll call a covering lemma. If anyone knows a better name for it, please tell me. But this is a very simple statement, just a simple geometric statement, nothing to do with codes actually. So let's say we are given a family of unit vectors in some, it doesn't even have to be finite dimensional, but some dimensional space. And the family also can be finite or infinite. And let's say another unit vector G. And the vectors in this family F form a cone around G in the sense that, yeah, they all have inner product at least epsilon. Then you can find a point H, which is in the convex hull of this family, such that the vectors also form a cone around H. The inner product suffers a quadratic loss. So if all vectors in F have a large inner product with G, then they also have a large inner product with some H in their own convex hull. This H is not going to be a unit vector. It's in the convex hull of unit vectors. It need not be unit, but it's a convex complement. And we'll think of this H as covering. Is the statement okay? So, the proof is not complicated. This is the whole proof. It just, in some sense, look at the maximally convex point, or so something which minimizes the norm. And if there is some F or some direction which is essentially orthogonal to this H or has very small inner product, you can move in that direction, reduce the normal. And this is just a quantitative measure. So yeah, I mean, you can prove it using gradient descent, you can prove it using the regularity lemma, you can prove it this way. There's many different proofs. It's very simple stuff. Okay, let's use it to prove the Johnson bound. And sorry, was that good?
Why? I mean, is it? I mean, I guess I'm just wondering, why is it epsilon squared?
Right. So in this generality, I think epsilon square is tight. If I look at the, let's say, coordinate basis vectors, if I look at k of them, and if I want something which is in their convex hull and has large inner product with all of them, then the best I can do is the uniform convex combination, which will which will suffer a quadratic loss.
I see. So I mean, so geometrically, it's just saying that there is a pointed cone, right, or something. Okay.
Yeah, exactly. So, but thanks for that question. So in general, this epsilon to epsilon square trade-off is tight. I mean, I can look at 1 over root k times the sum of all of them, which is some unit vector, which will have an inner product 1 over root k. But if I want something in the convex hull, the best I'll do is 1 over k. Okay. So now let's use it to prove the Johnson bound. And then I'll just kind of say why this already gives us an algorithm. So let's translate the objects that we have in the setting of Johnson bound all to unit vectors in some space. So we are given some x, which is possibly some corrupted code word. We want to just kind of look at a ball around it. So let's take this x, which is in F2, map the bits to 1 or -1. So again, map the 0 to 1, 1 to -1 if you want. And if you think of, let's say, the expectation measure on the coordinates of G, this is a unit vector. We can do the same for every point in this list. Remember, we don't know that the size of this list is bounded. We just know that these are all the points which are within distance delta. We want to prove that there are not too many of them. That's the statement of the Johnson bound. So for every z, we can again map it to a ±1 vector f sub z. Same mapping, 0s to 1s, 1s to -1s. And now distance kind of translates to correlation or inner product. So if x and z are at distance j of delta, then the inner product is 1 minus 2 times j of delta. So because they agree in 1 minus j of delta fraction and disagree the rest. Covering lemma will tell us that there is an H which is in the convex hull of all these list code words with inner product, which is the square of whatever that number is. And we chose this number precisely so that its square is 1 minus 2 delta with delta equal to distance. So that's what we have so far from applying the covering lemma. Statement. Okay, so far. This is just translating the notions to the setting of codes. And now I claim we are basically done. So I'll sort of just make 2 remarks. So one, H is in the support or it's in the convex hull of these list code words. We can assume without loss of generality that the size of this support is bounded by Cartesian theorem. It's an n-dimensional vector, n is the block length. And secondly, I'll claim that anything that is not in the support can't be in the list. Why? Let's say we take some f which is not in the support. Let's take the inner product. H is a convex combination. Let's write this inner product as a convex combination of these inner products. Fi is f sub z is not in the support, so it's always different from each of these Fi's. 2 different code words always have small inner product because of the distance of the code. So this is always smaller than 1 minus 2 delta. And so anything not in the support has a small inner product with H, but we assume that anything in the list has a large inner product with H. So the list has to be small. All right. So maybe this is a slightly different proof, or maybe you can translate the usual geometric proof to this one. But all I say is that this proof adapts very nicely to algorithms because all we needed about H was this property that if I look at some code word which is not in the support of H, then it has small inner product. And I'll basically replace H by an algorithmic proxy or sort of a convex proxy, which as long as it still satisfies some version of this property, we will be able to just convert this proof into an algorithm. And so we were looking for H in the convex hull of the code words, or I mean, convex hull of the list, but even the convex hull of the code words would be fine.
So, Madhur, I just one quick question.
Yeah, absolutely.
So in the previous slide, by Johnson Lindner's house, you can just make n something like.
Thank you. So if you want slightly below the Johnson bound, if you want like Johnson bound minus epsilon, you can make the list size actually 1 over epsilon square.
I see.
Yeah, so here I just use Cartesian, but you can use approximate Cartesian too. Yeah, thanks. Yeah, so all right, so we'll work with a convex proxy H tilde, which is some sort of convex relaxation. And as long as it satisfies this property, we'll be okay. And the convex relaxation we'll work with is the sum of squares relaxation for convex sets. And if you think of a convex hull, it's a set of distributions over code words. And instead of looking at distributions, which give you all kinds of moments, we'll only look at the set of low degree moments or set of numbers. And instead of saying list of numbers corresponding to low degree moments, linearly extended to polynomials, I just call them pseudo expectations, which is also a term we heard yesterday. These are pseudo expectations, which are dual objects of the sum of squares for the system. So they'll satisfy this kind of inequality that if you take these moments, try to use them to compute the expectation of some p-square, it should behave as if they were really moments, and this would be non-negative. And so these are the kind of formal axioms we have for working with them. So you'll get a list of numbers which can, or you can think of them as a linear operator on polynomials, and they'll satisfy non-negativity on squares, at least for low degree, and normalization. And we'll need some additional conditions which depend on the problem. The certain axioms are satisfied, but I'll just suppress that. In fact, yeah, stop this. So, and remember, all we needed was this proxy satisfies some notion of distance for the code. What's the distance of a code? It's just this quadratic inequality. That if you have f and h, which are two code words, then either they're equal, the inner product is 1, or it's smaller than 1 minus 2 delta. And we are going to relax h to a convex object. So basically, we'll need this inequality for every code word f. And if you can prove this, or if you can show that your convex relaxation satisfies this inequality, basically the same proof of the Johnson bound goes through, and you can actually show that the same sort of covering lemma goes through. So you can extract, I mean, this is a very simple toy example. Let's say you have covering lemma and this h tilde object satisfies that the inner product is larger than 1 minus 2 delta. Let's say it also satisfies this inequality. And in fact, that I can write this expectation of products as a product of expectations. Then, of course, it's kind of trivially true that the inner product of this vector, which is just the vector of first moments with f, is actually 1. And so I can just find the list code word just by looking at the moments. It's not quite true, but it's almost true. So you can get this to be approximately 1. You can get these to be approximately equal, not for the original pseudo expectation, but after kind of modifying it a little bit by picking the values of few variables. And depending on what values you pick, you get different elements of the list, but you can basically find all elements of the list or find some vector which is very close to them. And then, yeah, I mean, that reduces it to unity. Okay, and all we need to prove is that this inequality is a sum of squares. Again, I'll not necessarily give the proof, but I mean, if you know anything about the distance proof of these expander-based codes, they are using one fact, which is the expander mixing lemma. And the expander mixing lemma is just some kind of a spectral bound, which just says the size of the quadratic form is upper bounded by lambda times the norm, plus its correlation with the all ones vector. You can just write it in terms of the quadratic form of a positive semidefinite matrix, which is a sum of squares expression. So, I mean, yeah, once you kind of work through the proofs, this is true. And this can be extended to lots of other codes, some of which we did know this decoding algorithms through more specific frameworks, some of them we didn't. But yeah, this is an idea which works more generally whenever you can write the distance proof with the sum of squares. And yeah, I'll stop there. So, some sort of questions. I mean, one, this is a polynomial time algorithm, but not a great polynomial. And it's a far cry from the linear time unique decoding algorithms. You would actually like fast ones. And this was doable for some other codes where we had sum of squares based algorithms, but once you kind of understood the structures they were using, you could actually get fast ones. I don't know how to do it for this one. Can the same sort of ideas be applied to quantum code where the notions of distance, etc. are different? Some things can be done, but not all we want.
What is quantum AEL?
Okay. So there is a distance amplification procedure of Allen, Edmonds, and Levy, which can take any code and amplify it to some optimal code parameters. And we can show that if you do this procedure, then the resulting codes can be list decoded by uniquely coding the original. So you can get quantum codes which are list decodable, and we didn't. Okay. Right. I'll stop.
Is there any hope for like a local list decoding from this framework, or is that clearly not gonna happen because you can't succinctly address the SOS proof or something?
Not in this framework. I mean, one, already the codes I'm working with don't have enough redundancy built in for local list decoding. Usually you need very low rates for those. Secondly, I mean, yeah, SOS is a very global algorithm. Probably if you kind of understand the spectral structures underlying it and sort of extract some spectral algorithm, there is some hope it might generalize to kind of these low rate locally list decodable code, but not this framework.
More questions? Let's Kurt, the speaker.